Everyone, thank you. My name is Johan Pascal. I've been contributing on the Linphone project for the past 10 years, more or less, and I'm going to talk about the introduction of post-quantum cryptography in voice over IP soft phone. So quickly the agenda, first some context, then we'll dive into ZRTP protocol, and then how we had to modify it to use post-quantum cryptography. And then a few words about hybrid post-quantum and classic key exchange, and some conclusion. So first, some context for advertising for Linphone first. It's a project which is around for now more than 20 years. It's available on lots of platforms. The idea is that we have like a common library, and then on top of that, different applications for different platforms. It's try to use at most SIP standards and everything standardized, RFC and so on, for audio, video, instant messaging. We also provide secure group messaging. It's based on a derivative of Signal protocol that I presented here 3 years ago. We also provide a SIP proxy, which is called FlexiSIP, also open source, everything is open source, and I encourage you to use our free service on SIP, which is sip.linphone.org. Basically, I don't know if you're familiar with VoIP, but basically you have two streams of data. First stream is the signaling path, which connects the endpoints together. And then you have the media stream, which actually sends data, video, audio, encrypted. And this one we want to encrypt. So how it works, there is an RFC for that, and the protocol which is called ZRTP. And ZRTP is symmetric encryption, so far we are not very concerned by quantum computers. Main problem with that is that it requires an external key management, so we have to exchange our symmetric keys. So for that we have three choices. The historical one is called SDS. So on this one, the keys are transmitted in the signaling path, which if the signaling path is protected, which is normally the case by TLS, is okay. The only weakness is that the SIP proxy gets access to the symmetric keys. So we are not actually end-to-end encrypted. So basically, people running the service could decrypt your media stream. So there is another one, which also gets an RFC, which is called DTLS SRTP. Basically, on this one, on the media stream, you perform TLS handshake, actually a DTLS handshake, because it's over UDP. And this one works well, but you have to deploy a PKI, and you have to manage certificates for all of your clients and everything. So it's a bit heavy, and also you still have to trust someone. I mean, you trust certificates, sure, but still. And then there is another one that we favor. Well, all three are available in Linphone, but the last one, which is called ZRTP, is one on, we'll focus on this one today. And this one, on the media path, you perform ZRTP protocol, which is based on Diffie-Hellman, which using electric curve or simple Diffie-Hellman. This one has no third party required, so which is good. The only small thing is that you have to confirm, make some kind of spy thing that you have tell secret code on the phone, but as you are talking one with each other, for the end user is a bit an annoyance, but you have to do it once in the call history, whole call history with your other endpoint. So we think it's acceptable for users. Obviously, one has to get involved in security, but normally it works. I mean, the experience tells that people focus on security tends to not be driven away by this small drawback on the protocol. So it's an RFC which is now more than 10 years old. It has been mainly written by Phil Zimmerman, the guy behind PGP, which are always focused on avoiding third parties. And it provides different properties. I won't explain the key continuity and stuff because this one is unchanged. And I will focus on man-in-the-middle attack detection. So first, a small reminder of what is Diffie-Hellman. So basically, it's a protocol where it's completely symmetric. One part, both parts will generate key pair, and then they exchange public keys. And with this secret key and other side public keys, we'll get a shared secret. So far, so good. It's kind of easy. Only drawback is it's obviously vulnerable as many key exchange protocol to managed middle attack. So managed middle attack, what it is basically someone putting ourselves in the middle and exchanging keys with both sides. So the side cannot know, basically Alice cannot know that Eve is sending her key. She thinks that Bob is sending the key, and she performs the exchange, and at the end what you get is that Alice gets a shared secret with Eve, and Eve gets another shared secret with Bob, but Alice is convinced that she exchanged keys with Bob, and she has no ways to actually detect this. Well, she has actually some ways. No? Better? Yeah? Okay. No. Yeah, sorry. Where are we? So the ZRTP handshake is there is first phase of discovery. So what is happening is both endpoints will exchange their capabilities, their choice of preferred algorithm, stuff like this, and then start the actual ZRTP handshake. So first you have one packet of commit. I won't go in detail now, and then you actually perform the DF-Hellman exchange. So Alice is sending her public key, Bob is sending his, and they both compute from this. They will compute the shared secret, and adding all the transcripts of the communication, they will generate S0, which is the base secret, the output of the ZRTP handshake. From the S0, they will derive the ZRTP keys, which is what we are trying to do here, and they also derive something called SAS, short authentication string, that will be vocally compared over the phone, because Alice and Bob are actually talking to each other. So the end of the protocol is just some updates and writing in cache for key continuities mechanism and stuff that's not really interesting now. And then after that, the ZRTP streams start actually, and they can talk. And once they start to talk, once in the call story, they will do this vocal SAS comparison. What it's for? This SAS comparison is basically if they want to detect man-in-the-middle attacks, they have to ensure that Alice is using the keys that Bob has sent, and also Bob wants to know that the key that was sent by Alice is the one he actually got. So what they could do, as they are talking, they could basically read their own keys to the other. But the key is something which is few hundred bytes, so it's a bit long to read few hundred bytes of hexadecimal chain over the phone. No one will do that. So what they do instead, we derive this short authentication string, which is only 4 digits, and has 20 bits, actually derived from 20 bits. And this SAS is also derived from the secret 0, which is the output of the protocol. The only problem with that is that you can actually perform a SAS collision with that, because the SAS is very short. How it will work? So actually at the beginning of the protocol, as soon as Alice sent a public key to Bob, Bob is able to compute S0 because he has his own secret key, and he is able to compute the SAS then. So what one could do is that Eve performed first the ZRTP exchange with Alice. She got the SAS one, and then she received Bob's public key. When she got Bob's public key, she can generate a huge set of key pairs until she finds a SAS that collide. Basically, she will try a lot of, she generates pairs. SAS is only 20 bits, so if you generate 1 million keys and try all of them, you will for sure find a collision of the SAS. So to prevent this, Eve is forced to send a commit packet. In the commit packet, what we have, we do not have our public key, but we have a hash of the public key. And so when you receive the hash of the public key, Alice will receive, for example, Bob's hash public key. She'll store it, and then when Bob sets the public key, she will compare. She will just hash Bob's public key, and she'll compare. So that way she's sure that Bob did not wait for receiving her public keys and cannot generate millions of key pairs to find the collision on the SAS. So this is quite effective, and so far so good. Now we want to switch to use post-quantum cryptography. Problem with post-quantum is that on the NIST call for standardization, they required all the algorithms to use key encapsulation mechanism and not DF-Hellman. So key encapsulation mechanism is a bit different because there are two sides are not the same. In Diffie-Hellman, the two sides were exactly doing the same thing. They are both generating keys, exchanging public keys, and then computing secrets. There we have one side generating keys, one side encapsulating the key, a secret, and the other side will be able to decapsulate the secret that was encapsulated by the first one. So it's not symmetric, so we cannot switch directly from Diffie-Hellman to KM form of key exchange. Obviously, KM is still vulnerable to man-in-the-middle attack because nothing has changed. You can still put someone in the middle and perform the exchange with the other side without them knowing. So what we had to do is adapt the ZRTP and change a little bit the actual handshake, so the central part of the protocol. So S0 is still derived from the exchange secret and transcript of all the conversation. I wrote only commits and 2 packets, but you have also hello packets and stuff. So in the commit packet, the one which used to hold only the hash of the hash part of the second packet from Bob will now insert his public key. Why will he do that? So Alice can encapsulate the secret. So at this point, Alice receives the public key from Bob, she encapsulates the secret, but at this point she's not able to compute S0 because she's missing the second packet from Bob. So she'll send back the ciphertext, so the output of the encapsulation, but at this point she has the shared secret from the key encapsulation, but she cannot compute S0. Bob now retrieves the shared secret, and he can compute S0, but he already committed on the H2 that he has to send to Alice, so still he cannot manipulate the secret, the final secret, the S0. And what is in this packet? It's just a random number that is used once. Okay? So now, another problem is that we don't want to focus only of using only post-quantum algorithm, because we know that sometimes they got broken, like for example Psych, which was broken a bit late in the standardization process. So it might happen or not in the future. So to protect against this weakness, its possible weakness, we still want to use a mix of post-quantum and a classic algorithm. So we'll use both at the same time. And in order to not complexify the protocol too much, the idea is to have one version of the protocol which is doing Diffie-Hellman, and the other one key encapsulation mechanism. And they don't have to, the protocol won't know exactly if it's using a mix or not, because probably in the future, at some point we'll be confident enough with some post-quantum algorithm, and then we'll stop using the classical one, maybe or not. But still the protocol should not be modified at this point. So the protocol is done to use a KM interface without even knowing if it is a mix of classical and post-quantum, or just post-quantum, or several post-quantum. So first we have to make a KM interface from Diffie-Hellman. This is quite a standard construction. You generate, instead of, you can directly use the Diffie-Hellman construction to generate key pair. Then you can send your public key to the other side. The other side will encapsulate. How would the other side do that? It would just generate an ephemeral key pair for Diffie-Hellman, compute the Diffie-Hellman, and then hash it with the transcript of the exchange, and send back his public key to the other side. So the encapsulation is quite obvious, same thing on the other side. And then we combine 2 or more KMs together. The one we just built from a classical Diffie-Hellman or elliptic curve Diffie-Hellman with post-quantum one. So this way of doing it has been published by Nina Bindel, sorry, I'm not sure how to pronounce the name, a few years ago. So it's a bit convoluted, but if you want more details on why we are doing this, I encourage you to read the paper. It's quite interesting. So basically what you do when you generate a key pair, you generate key pairs for a set of algorithms. In my example there, it's only 2, but you can do more of that. And send concatenated both public keys, or all the public keys, to the other side. The encapsulation will just split your public keys to retrieve the individual ones, and perform the encapsulations on all the components. Then you use hashmap to combine your results, chaining it. So first you combine key 1 and then key 2, and you can add several layers there. And the final step is to use the transcript, all the public keys you received. And the decapsulation is obviously completely symmetric. Right. The paper from Nina Bindel is quite clear on why these steps are needed. I have no time to explain it here. Few more words. We also had to tweak the protocol packets because in the defilement form, the maximum size you can get is around a few hundred bytes. But if you start using Kyber, for example, or HQC, the one we used, you'll reach several kilobytes. And several kilobytes you cannot send in one datagram over UDP. It's not possible. You probably won't arrive. So what we had to add is a way of fragment the ZRTP packet. So it's kind of classical way as just as DTLS is doing it or other protocols using UDP. The only thing is that we made it in a way that packets are not fragmented and the header is modified, but if it's not needed, the packet remains exactly the same than the old packet. The objective in this was to be able to start deploying the new version of the ZRTP, but still keep compatibility with the old one, old deployments. So how it's done in the end, we use crypto libraries liboqs, which is from the Open Quantum Safe project, which basically collects all the NIST candidates and Kyber also, which is no more candidate, in a convenient way. And we use libdecaf and embed TLS for the ECDH and hashmap functions that we need. So we packed it all in an independent module. So our ZRTP library will use this module, but it's completely independent actually from it. So if anyone wants to directly use this hybrid KM mixing varieties of post-quantum and classic exchange, it's fully available. You can combine usually more than 2 KMs as it was printed. It's written in C++. And in our ZRTP implementation, we deployed it with some already preset combination. So we have well, you can see them until read them. We try to mix algorithm with more or less the same level of security. So mixing the Kyber 512 with X250, this one. And it is obviously, as I said before, fully compatible with the older version. So the deployment is progressive. It's basically in the agreement phase at the beginning. If both parties support this version of the ZRTP with this algorithm, they will use it. If one is old and don't support it, they will just fall back on classical defilement or electric curve defilement. So just how it looks like. First, you have the ZRTP handshake going, and the call is starting. And once the call is started, if it's the first one, the two endpoints are calling each other, you'll get a pop-up that asks you to confirm the security string. So both parties will just confirm it. Just say it on the phone. It's like, hey, it's written like you have to say this. The other one confirms you said what it's expecting to say, and you confirm it. Then this will be saved in the ZRTP cache, and you will never be asked again to do that. At any time during the call, you can check on the call stats and see what kind of algorithm you use to perform the exchange. So on the screenshot, you see that it was using Kyber 512 and X25519. Here are some links, just if some of you download the presentation, towards the Linphone website, directly pointing to the GitLab, where you can find the source code of both the ZRTP and our post-quantum crypto module, and to the publication from Nina Bindel explaining how to hybrid several crimes. Here we are. Thank you for your attention.
Okay, so we've got time for questions, and I've got one question on metrics, and there is a question why post-quantum encryption is not enabled in the precompiled Linphone SDK.
Sorry, I didn't.
Why the post-quantum encryption is not enabled in the precompiled Linphone SDK?
It is now.
It is now? It is now. Okay.
It is now. Yeah.
Based on
Yes, sorry.
Hi. Given that we're dealing with threat actors that might be capable of cracking quantum cryptography.
Sorry.
Okay, given that we're dealing with threat actors that might have a lot of resources, it seems like one particular attack vector might be to essentially use real-time deepfake technology to intercept the vocal SAS comparison. Do you see any particular mitigation for an attack like that?
Well, some kind of attack like this has been already studied and published. So basically what came out of what I found is that it's kind of easy to synthesize, to use speech synthesizer to synthesize the voice of someone else. The main problem there would be to insert the SAS at the right moment in the conversation without adding a huge delay in the conversation so that people won't be able to talk. Basically, if you add like 2 to 3 second delays because you have to analyze the signal and like buffer it to be able to insert back your SAS, people won't talk with 3 to 4 second delays. There is no way people will keep talking.
I agree. I think it's going to be very difficult to do something like that in real time, but I think that's probably because your solution looks really, really solid in terms of being able to fix it like that. So it looks like that might be one of the weaker aspects of it, but it's
since now I've been trying to monitoring publication on the subject, and I never found someone able to publish an actual attack on ZRTP working really. So it might happen at some point.
That's great. Thank you.
Can we be quiet during questions, please?
Thank you.
I think I missed it, but then in this particular method that you are doing, is it actually trusting the middle server that you're using, or is it using the keys from another, like a phone or something? SIP, assuming, is this running with the SIP protocol you said?
Wait, yeah. I'm sorry, I cannot.
Hello?
The sound is very low.
Hello?
Better, yes.
Yeah. So I wanted to ask if this was being used with a mobile phone to connect to the SIP server and then use post-quantum cryptography as you demonstrate. Can you go back to the 2 slides before, please? Yeah.
What is
this
one?
one? Yeah, so the phone, is it actually trusting the server which is running, or is it like the end-to-end? The actual key is being checked with the other host?
Yeah, this is the main point of the ZRTP, that basically the idea is to not trust anyone, not your server. So the server will be in charge just of connecting the 2 phones, and then the media will go directly from one to the other one. The media pass will go straight from one phone to another one, and it won't go through the server. And that's why the ZRTP exchange is performed on the media pass and not on the SIP signaling pass. When you establish a connection, actually, you'll go through ICE protocol. I don't know if you're familiar with that, which basically find a way to connect directly. Because at the end, you don't want the media to be relayed, because you lose too much time. You have to send media packets directly from one endpoint to the other endpoint.
Hi. You said that you have to compare the SAS only once.
Yeah.
Is it once per phone or once per user?
It's one per endpoint. Basically, in each endpoint, you have a cache of previous. Each time you end a ZRTP exchange, you'll keep some shared secret that you'll use the next time. And so during the exchange, at some point you will compare this shared secret, and if they're the same, you'll use them to compute a SAS, which is always available. You can always ask to compare the SAS. But it won't pop because the protocol will know that you performed the exchange before. But it's just from one phone to another phone. This cache is not shared.
Okay, so in practical terms, if I buy a new phone and install the same app with the same account, I have to do it.
You have to do it again with all your correspondence.
Okay, thanks.
We've got time for a last question. Is there any other last question? If not, thank you for your talk.
Thank you.